In this video, I want to talk about one of the more useful tools in calculus where we try to maximize a function or minimize a function. Um, we're always trying to maximize the profit or maximize efficiency and minimize costs and minimize waste. All of these things are very useful to figure out in real life context. And when we have these multivariable functions, we want to be able to figure out how to work out what would be the best way to get the best out of this function and so on. So let's look at this very useful type of tool, optimization problems. Okay, so some terminology here. We want to talk about relative extremes. So we say something is a local maximum where the value of the function at AB is greater than or equal to all nearby points fxy. So basically, the surface looks like a hill, and at the tip is at the height of FAB, and all nearby points are lower on the hill, lower height. So when you have a situation like this, we say it's a local maximum. We say local because there could be a higher mountain behind somewhere. But at least when you look close by, it's a maximum. There's a similar definition for local minimum where there's a small valley. It doesn't have to be small, but if you look at a point, it's the lowest point if you compare it to all nearby points. Those are local minimum. Okay, and at those points, one thing you could say is that the derivative should be equal to 0 because if you can find partial derivative that's either positive or negative, you can follow that slope and get a slightly higher number or slightly lower number. So you can always kind of move a little bit to change your value more towards the maximum or more towards the minimum. The only time when you can actually be on the top or bottom of a valley is when the derivative in all directions, all the directions is equal to 0. So that's when gradient is equal to 0. So those points are called critical points, much like we discussed in Calculus 1. Okay, so let's remember the gradient is vector with partial derivatives. And all of these derivatives has to be 0 at the exact same time for it to be a critical point. So if I'm given a polynomial like this in 2 variables, it's not at all easy for me to graph this or work out where the hill is going to be. I don't have a good guess. And even worse, if there's third variable, I can't even see that graph because I don't have enough dimension. So I want to be able to rely on algebra when something like this happens. So let's first compute the derivative with respect to x. So if I take the derivative with respect to x, that's 0, 3x squared. And derivative of y cubed is 0 because I'm taking derivative with respect to x minus 3y. Okay. And I want the derivative here to be equal to 0. So I'm going to set it equal to 0 and solve for x and y. But here I just have one equation with 2 variables, x and y. So I can get what the x and y value is supposed to be. Let's look at the partial derivative with respect to y. You get 3y squared minus 3x. Okay, equal to 0. So what can we do here? So I want both of these equations to hold at the same time. So maybe I'll bring 3y, negative 3y, to the other side of the equation. Okay, and get y is equal to x squared. And then maybe I could take this and substitute it in for y into the second equation. Okay. Both of these terms has 3 with it, so I'm just going to divide both sides by 3. Okay, if I bring x to the other side, I get x to the 4 is equal to x. So if x is equal to 0, this is a solution. So if x is equal to 0, then 0 is equal to 0 to the 4th power, so this works. And if x is 0, then y is 0 squared, so y is also equal to 0. So 0, 0, the origin is one critical point. If x is not equal to 0, then I can divide both sides by x. So x to the 4th is equal to x. If I divide by x, I get x cubed is equal to 1. That means x is equal to 1. And then if I work out that x is equal to 1, I can plug that 1 in here and get y is also equal to 1. So 1, 1 is also a critical point. So this problem has 2 critical points, 0, 0, and 1, 1. Okay. All right. Here's another problem that you could try your hand at. It's slightly harder, but not too much. You can pause the video, try it out. It's a good algebra practice, I think. And when you're done, you can unpause the video like now. And the solution, this one has 3 critical points, 0, 0, square root of 2 comma 1 half, and negative square root of 2 comma 1 half. So I think this would be a good practice problem. So try it out. Okay, so if you have a maximum, local maximum or local minimum, it has to be a critical point. But just because it's a critical point doesn't mean it's a local maximum or local minimum. So you kind of narrow it down into key points that you should focus on, but it doesn't tell you if, oh yes, this is a maximum or not. So the way to do that is using what's called the second derivative test. So let me describe it. It sounds mysterious at first, but I can maybe convince you that maybe this is true. Okay, so let's see. Suppose AB is a critical point of F, and we have second partial derivatives that are continuous on this region surrounding AB. And we compute this number called D of AB. Now, this quantity is going to be computed by a combination of different second partial derivatives. Here it's fxx times fyy minus the mixed partials fxy squared. Okay, so you compute this number, and depending on the sign of this number, it tells you whether you have a maximum, minimum, or neither. Okay, so if you get a positive number, and also the second partial derivative in x direction happens to be positive, then you have what's called relative minimum, right? So it's at the bottom of a dip. Okay. if quantity d is positive and the second partial derivative in x direction is negative, then what we have is a relative maximum. So it's at the top of a hill. If this quantity d is negative, then it's definitely not maximum nor minimum. It's what's called the saddle point. So it, it looks like function is increasing in one direction and it's decreasing in another direction. So there's it's neither maximum or nor minimum. If this quantity d happens to be exactly 0, the test is inconclusive. It could still be a maximum, it could still be a minimum, it could still be a saddle point. The test doesn't tell you which is true, unfortunately. Okay, so what I want to do is kind of give you an intuition for this quantity d that just seems to come out of nowhere. So it seems like if it's positive, then you have a maximum or min. If it's negative, then it's all twisted up and gives you a saddle point. I want you to see there's a square here, right? The mixed partial derivative is being subtracted from the quantity. So because the square is always positive, if you're subtracting a square, this portion is always bringing it more towards negative side. So the only way this could end up as positive is when these two non-mixed partial derivatives, so fxx and fyy, are both the same sign. So if they're both positive and multiplied together, it's a positive number. If they're both negative, then the sign cancels out and you also get a positive number. If they disagree, then there's no hope, right? Like if they have opposite signs, then the product is negative, and you're subtracting more quantity from it, so it's gonna be negative. It's a saddle point. Okay. So what does it mean when the sign is the same? So that means it's concave up in x direction and concave up in y direction. So in both directions, you're concave up. So it makes sense that this is a local minimum. If they're both negative, then there's a little hill, and then there's a local maximum. And then if they disagree, you're going to get this kind of saddle point here. But you might wonder, well, if they match the sign, if they're both positive, for example, how could it ever be a saddle point, even if this quantity is big and you subtract away enough so you end up with a negative number? Well, this mixed partial derivative fxy kind of measures how twisted the surface is. And it's possible to have something that's kind of curving upward in x and y direction, but surface itself is twisted. So you have a saddle. Let me show if I can have like a graph that could show this. Okay. Let me share screen. Okay. So let me kind of try to draw, have a graph for us. So x, okay. So let's start with paraboloid. So if you have z is equal to x squared plus y squared, you have this bottom of a valley. So this would be a local minimum situation. And let's see what would happen as we take this surface and twist it more and more. So this will have positive fxx and fyy. But let's twist the surface a little bit and add x times y. Let's see what that does to the graph. Okay, so you twisted it in a diagonal direction. It looks like a ellipse, but there's still a local minimum there. So let's twist it a little bit more by multiplying by 2. Here, it's twisted it enough where diagonally it's flat. If we twist it even further, you can kind of see that it's starting to bend backwards in a diagonal direction. And here it's definitely a saddle point. Okay. And now it's definitely a saddle. I don't know if I can rotate this picture. I don't think I'm allowed to. It has, so paraboloid has turned into now hyperbolic paraboloid. If you look at the contour plot, you can see this X where in one direction it's going higher and higher, in another direction it's getting lower and lower. So there's a saddle there that's happening there. So that's just graphing, but trying to give you an intuition of exactly what second mixed partial derivative is doing to the graph. So it twists it somehow. At least that's how I keep it in mind. Okay, so I think I want to end the video here. So some of you will probably be not satisfied with this video. I gave you a second derivative test and how to apply it, but I haven't given you a proof yet. So I think I'm going to record the proof in a separate video. It doesn't add too much to the insight of what's going on. I think this experiment of graphing is giving you more than what the proof might give you, but I think some of you would like to see the proof and see how it's logically that quantity will give you whether or not there's a local max, local min, or saddle point. So I'll leave that as a separate video. Oh, I completely forgot, sorry. Before I end the video, let's actually test this out. So we had an example earlier of critical points, 0, 0, and 1, 1. Let's work out if this is a local max or local min. Let's do that. So to do the second derivative test, I have to compute second partial derivative. So fxx, so here's fx. So if I take the derivative with respect to x again, I get 6x. Fyy is going to be 6y. And then fxy is equal to -3. Okay. So let's compute the quantity d. So in our case, it's 6x times 6y, so 36xy minus -3 squared. So subtracting 9. We have two critical points, so let's look at 0, 0. So if I plug in 0 for x and y, I'll get a negative number. Okay, so this means that this is a saddle point. Okay, let's see what we would get if we plug in 1, 1. So if you plug in 1, 1, let's see, we will get 36 times 1 times 1 minus 9. So 36 minus 9 is 27, which is positive. And fxx is 6, which is positive. So if both of these are positive, what we have is a local min. Okay, just to point out the test here, if it's positive here and positive here, we have a relative minimum, which is the same thing as local minimum. Okay. So I want maybe if you have time, you could try this out on the second function here as well. You could try it out. You should get local min here, and these two are saddle points. So I'm not doing the computation here, but I want you to try it out to verify that this is true. So that's what you should get for this problem. Okay, I'm gonna end the video here. If you'd like to see the proof of the second derivative test, I will post the video for the proof. And it is not, the expectation is that you don't have to understand the proof. So if you don't care to look at the proof, I don't mean to bore you with it, so you don't have to watch that video. But I think probably about 20% of you would like to see exactly how that is proved. So if you're curious, you can look at the video. All right, I'll see you later.